done. All right, it's recording. Exercise 10EF is just two. Remember, chapter 10 is applications of calculus. So we've done tangents, we've done normals. Okay, that was your A and B, rates of change as well, average rate of change. And then previously we did, what did we do the last lesson with all the exam questions? Yes, kind of hinted that. But this one is actually the maximum, minimum, absolute max, absolute minimum. So what was the difference between local minimum, local maximum? Local minimum is just talking about where is the stationary point occurring. So what types of stationary points you have? Oh, that was the previous lesson. Stationary points. So local max, local min. But an absolute max and absolute minimum problem is asking what is, so find the local maximum when you let delta y, delta x equal to 0. That's your stationary point. But absolute max and absolute min is literally just the highest or lowest point anywhere on the curve. Okay, that should be and the lowest point anywhere on the curve. What's nice about this kind of problem that examiners like, or what you'll be experiencing in 10E and 10F, is that because you're usually not allowed a calculator, unless you're doing a CAS component, then that wouldn't be part of it. But what's nice is that they give you a function, and you don't normally can picture what that looks like immediately. So because of that, they only tell you the domain, and they want you to tell them, well, what is the lowest and highest value? That's essentially it. If we could see the graph, we could probably figure it out straight away. But because we can't see the graph, then what are some things that we can use as our tools to predict what would the lowest and highest values be? Now, one of the first things is, whatever this graph is, there's an endpoint. There's 2 and 3. So wherever those 2 and 3 is, if you look on an x-axis, for example, 2, 3, I can kind of figure out the y values to kind of guess, well, it could be here, it could be there, hypothetically. Then I would say, well, the y value at 2 is currently the highest, and the y value at 3 is currently the lowest, hypothetically, right? But then we also know that there could be a local max, a local min. Maybe this graph goes up and then up and down. I don't know how many curves they have before they get back, right? So if it goes up, it goes back down, goes back up, it goes back down, then 2 is no longer the maximum, but it's actually that local maximum. There's the highest value. So that means we got to then check for stationary points. Does this graph have any stationary points? And if it does, what is the y value at those stationary points? And we find the highest and lowest y values. So we take y values at the stationary points and the y values at the end points and compare. That's what's special. So without the graph, you have to then visualize with the little tools that you have. So to start off, I've given you a guide, or at least the exercise gives you guides on how to do it. Normally in the exam, they don't give you these guides. They just literally ask you absolute max, absolute minimum. Yeah? So here, let's find the derivative. So again, this is tech-free. I don't want you to use a CAS. What is the derivative of f of x? Right now, we've got f of x. I'm going to pause the video for you to have a go first. Derive the inside. So derive the inside for the first one. Derivative of x minus 1 is just 1. So really, I don't need to write the 1 at the front. And then derive the outside. So bring the negative 1 down and then minus 1 by 1. So you should get x minus 1 to the power of negative 2. Hands up if you've got that for the first bit anyway. Okay, good. Then the second one, if you derive it again, derive the inside. Notice derivative of negative x will become negative 1. So that means there should be a minus 1 on the outside. So this one, I didn't write the 1 because the derivative of x is just positive 1. And then, again, minus 1 take away 1 is minus 2. Okay, and that still is 4 minus x. So this is the derivative, but I would normally rewrite them as 1 over x minus 1 squared, and then take away 1 over 4 minus x squared. Hands up if you got this one correct. I probably would have combined them as well, just because I can see that the next one, when you're solving. Yes? No? Oh, sorry. So far, so good? Oh, sorry, I forgot the negative 1. Thank you. And that should be a plus. So many mistakes. All right, thank you. what I would do next is I would actually combine them as one fraction. And the reason why is because if you're going to let it equal to 0 and then solve, having two terms makes it harder. So I would actually like to combine that using cross method. So if I add them all together, that becomes now negative of 4 minus x all squared plus 1 times x minus 1 all squared all over x minus 1 squared times 4 minus x squared. You don't have to do this, but I do think it's going to help you in the next step. Okay? So all I did was I just times both top and bottom by the opposite bracket, and then times top and bottom on this side by the opposite denominator. So for those who aren't sure what I just did there, I just times the bottom by x minus 1 squared, times the top by x minus 1 squared, times the bottom on here by 4 minus x squared, and then times the top by 4 minus x squared. That's all I did. Okay? Now, next question. See if you can solve it. I'm going to pause the video. I'm going to give you another 2 minutes. Okay, team. So, let's look at the logic. Shh. So remember, the first two parts was just more of a guidance question. The real question was actually part C. Find the absolute maximum minimum of the function. That's what they actually wanted you to do. Part A and part B was a guidance one. So we've just found the derivative. We found the derivative, which is stationary point. We found stationary point at x equals 5 on 2. Let's visualize what's happening here. Usually with max mins, I like to visualize it. You got 2 to 3 as your domain. You found that 2.5 or 5 on 2, which is actually dead center, that there's a stationary point there. Now you need to find the absolute max and absolute minimum. So the first starting point is, well, let's figure out what the y values are for 2 and 3. So what you're looking for is, what is f of 2? What is f of 3? And then I also want you to find out, well, what is f of 5 on 2 or 2.5? Because that's what we're trying to compare. And then we can kind of predict what the graph looks like. And then you can sketch it to see if it's true. But I'm pretty sure if you've done it with that domain, you can probably predict what the graph roughly looks like. Okay? Now let's go back to the original function, f of x. So that's what? 1 over 2, take away 1, plus 4, take away 2, gives you 1 plus half. Q. All right, as you're doing it by hand, it's a lot of fractions there, but hopefully your fractions are okay. First two was pretty straightforward. 3 over 2, 3 over 2. Do you understand how I got 2/3 here? 1 divided by 1.5? Yes, or 1 divided by 3 over 2. So for those who aren't sure, 1 divided by 3 over 2 is the same thing as writing 1 divided by 3 over 2. 1 times the reciprocal. That's how I got 2/3. Okay? So that's all I did there. 2/3 plus 2/3 is 4/3. So now if you put it into this diagram, at 2, I get 3 on 2. So the y value is 1.5. 3 is also the same. And 4/3 is about 1 1/3. So 1.33, roughly. So it must be less than 3 and 2. So somewhere here. So if I looked at that now, the graph must be something that it comes down and has a turning point, a stationary point, and it comes back up. So I expect it to be some sort of cup. So hence, max value that you can get is 3 on 2, absolute max. and absolute minimum must be 4/3. So far, so good? So if that was something on a CAS, it would have been quick and easier. You could sketch the graph, find the max, find the min. But in this case, these are the kind of questions you're going to be working with. You use the stationary point and the endpoints to predict. Have a go with this next one. Next one is much easier because less fractions and much easier to derive and all that. Find out the maximum, find out the minimum. And on the next page, the last problem is fun. That one's called, I'll guide it a lot in the solutions there. Let's see if you can work out the next bit from behind. Answers. Did you get something like this? You didn't have to find the derivative because we can read the turning point from the graph. So clearly, once you got the graph, you can tell what is the lowest value and what is the absolute max. So you should have got absolute max as 12. Remember, not 5. It's the y values. And absolute minimum should be not 1, but -4. Cool? So that's a nice quadratic, simple, easy one. But like I said, most of the graphs, if they want to challenge you, they'll give you one that you can't visualize. Then you have to find the derivative, sub in the endpoints, and then figure it out. Okay? Now, once you're ready, flip over the next page. I'll give you about 10 minutes to have a go, and then I'll guide you through it. But it's a pretty fun one. You're finding the area of a trapezium given only the hypotenuse and theta. How would you figure it out? So I'm going to flip over. Here's your problem. I've guided you-ish to give you hints along the way if you know you're on the right track. Yeah, I've given it to you there. It says area of trapezium. Answers. Did we at least understand the first bit? First bit where the angle, let's just rub all these annotations off. We can say that this angle is going to be symmetrical because they're both hypotenuse of 4. So you can see radius 4, radius 4. So that must mean this is also the same over there. Okay? So the first part is I just said angle AOB is equal to DOC. That's what I'm trying to say. If this is 4, which is the radius, then this is also 4, and that's also 4. So hence 4, 4, 4, 4. This is a perpendicular bisector, so it's a vertical height. So it cuts it right there. We can say that's cut in half. 90 degrees, 90 degrees, and it gives you this right angle triangle. So I tried to draw the right angle triangle on this side here. And we can see that that perpendicular bisector gives you the horizontal length on the top. That's your adjacent. How do you find your adjacent? Cos of theta equals to adjacent divided by hypotenuse. You rearrange it. Adjacent will equal to 4 times cos theta. So I can already say now in this diagram, this is 4 cos theta from here to here. That also means this is also 4 cos theta. How did I know that these two angles are the same? It's alternate angles. So this is that angle or elevation depression. Same thing. So you get 4 cos theta, 4 cos theta. And the height. Height is 4 sine theta. Okay, so from here, 4 sine theta.
It was a video and she keeps...
Alright. Shh. So now that you got the first component, then when we're answering area of a trapezium, it's half times A plus B. A and B are your two parallel lines. So on the bottom, it's 4 plus 4, so it's 8. On the top, it is double of 4 cos theta. Height, which we know is 4 sine theta, so that's what I did. I just said this is now 4 double 4 cos theta plus the bottom length, which is 8, times 4 sine theta. If you put it together, you can see 4 times 4 is 8, but 8 and 8, you can take out 8 as a common factor. So you get half times 8 common factor, and that gives you cos theta plus 1 times 4 sine. The 8 is length of the bottom, so A is double that plus that. So that's my B times my height. Yeah. So going back, here we go. We can see that half of 8 is 4, and 4 times 4 is 16, so that's how I've got a 16 here. And then sine theta is there, and cos theta is the same thing, saying 1 plus cos theta. So I was trying to give you a hint that you're on the right track, if that's what you simplified to. And even if you didn't get the first bit, you can still move into the next bit. We're trying to find the maximum area that this trapezium can have. So the max area would be when delta A, the area by delta theta. So that's the area function in terms of theta. So delta A, delta theta, you're going to have to use product function, because I can see that it's the product of 16 sine theta times 1 plus cos theta. So I can call this U, and I call this V. So if I do that, derivative of 16 sine theta would just give me 16 cos theta. And derivative of this is negative sine theta. Moving down, I filled out most of it for you there. VU dash plus UV dash. So V, Victoria University first. VU dash times UV dash. Which part?
I don't understand why we need to do it.
Oh, because the question was asking for the max area of the trapezium. So to find the max area, we know that when there's a stationary point in terms of the area function. So as the angle of that 4 increases, there's a certain point where you get the max area. So the question is, what would the maximum area be? So then I found, instead of a function of that, to find the maximum, I just found the derivative to find stationary point. All right. So from here, put it all into the equation. We multiply them together, and what I noticed is that they both have a 16. So I took out 16 as a common factor. So you're left with 1 cos theta times cos theta. And the other one is sine squared theta. I use square brackets to separate from the double brackets, so it's less confusing. Okay? Now, from here, we can expand, and that gives you cos squared theta plus cos of theta minus sine squared of theta. So I'm expanding it. But I noticed that sine squared of theta, there was a property that you learnt in chapter, whatever it was, on circular functions. Because this is in cos theta, you can change the sine squared theta so that they're all in the same function. So if I change them all into cos theta, that's a cos squared theta, that's a cos theta, it's sort of reminiscent of a quadratic. So I can change that. That'll be key. Now we know that there was a property, Pythagoras' theorem, cos squared theta plus sine squared of theta has to equal to 1. So that means sine squared of theta must equal to 1 minus cos squared of theta. So here I fill it in. I say 1 minus cos squared of theta. And for those who forgot, I was hoping this bit kind of hinted it out. So as you expanded it, negative times 1 is negative 1, and negative times a negative becomes positive. Now we can see that cos squared theta plus cos squared theta, there's 2 of them. And that gives you, on the top here, we can now fill it, I'll just fill it down here. But that gives you 16, 2 cos squared theta plus cos of theta minus 1. If it helps you, try to think of cos squared theta is x. You can call that whatever letter you want. You can call that a if you wanted to. But then we're really just trying to factorize what is 2a squared plus a minus 1. And if you factorize that, you should get, what's that, 1 and 1, positive 2, take away 1. So something like that. But replace the a with a cos theta. Okay? So in the next part here, I was trying to guide you guys. And so from here, the derivative is 16 2 cos squared theta plus cos of theta minus 1. Max area occurs when the derivative equals to 0. Here we go. I factorized it for you before, so it should have been 2a, which is cos of theta. Was it plus 1? Minus 1? And then cos theta plus 1. Yes, that works out. That's how I got this bit. Cos theta plus 1 is equal to 0, or 2 cos theta minus 1 is equal to 0. Solve for it. You then have cos of theta is equal to half, or cos of theta is equal to negative 1. Therefore, theta equals cos inverse of negative 1. It's either 180 degrees or pi. Cos of what angle will give you half? You got 60 degrees or pi on 3. So that means in that trapezium, in that circle, the angle that we're talking about is currently in quadrant 1. Can't be 180 degrees. Doesn't make sense. You wouldn't have a trapezium. So because of that, this can't be the answer. Theta must then be 60 degrees or pi and 3. And hence now that we know when would the maximum occur, the maximum area would occur when the angle is 60 degrees. So hence, going back to your original function, what was it again? Where's the original function? The area was on this side. Here we go. That's your area. So 16 times sine of 60 degrees times 1 plus cos of 60 degrees. And that's root 3 on 2 over here times by 1 plus half. And what you're trying to work out is 16 times root 3 on 2 times 3 on 2. 2 times 2 is 4, and then 16 divided by 4 is 4. That's 4. So you end up with 4 times 3, root 3, which is 12 root 3. Squared units. Big question, but it was a nice question.